All right, so I would like to walk you through the process of learning how to do binary number systems. All numbering systems, this is something they don't teach us in elementary school, and I wish they did. All numbering systems are built upon the same principles. Our columns increase by a certain factor. If we think about base 10, or what we call the decimal system, um, and by the way, I don't know if you've ever been told this or not, but the reason why we as humans used numerically base 10, that we count to 10 and repeat from there, and everything's built on tens, is because, plain and simple, we have 10 of these. There is no other better way than that. We could use any numbering system. In fact, if you look through ancient civilizations, they use a wide variety of different numbering systems. But we count to 10 because we have 10 fingers, we have 10 toes, and it works. But any numbering system would work. It's just a matter of use and what we'd be accustomed to. So our columns, which when we say numbers in decimal, if I said 5,642, I'm saying what those columns are. That means 5 times 1,000. It means 6 times 100. It means 4 times 10. It means 2 times 1. Those are our columns, our ones place, our tens place, our hundreds place, our thousands place, so on and so forth. All numbering systems are built on that same idea, that columns are related to something. And notice each of these increases by a factor of what our base is, base 10. So if I look at this numerically, not in terms of 1, 10, hundreds, and thousands of just decimal, but I think broad scheme in terms of what could these columns be with reference to any numbering system, I think about what they could be. How could I get a 1 if I'm thinking about the number 10? If I start with my base, what could I do to the number 10 and make it equal a 1? Well, if we know our math rules, any number to the 0th power is going to get you 1. And if I want to go from base 10 to the number 10, I can just raise this to the 1 power, and I still get my same number, which would be 10. And if I want to get from 10 to 100, I can take this times 2. And if I want to get from 10 to 1,000, I can take this to the, I shouldn't say times 2, squared, cubed, so on and so forth. So actually, our columns in decimal are really mathematically built by taking our base number and raising it to the power of its place, assuming we count starting at 0. So our 0th place, our first, so on and so forth. So our 1's column is really 10 to the 0th column. Our 10's column is 10 to the 1st, and so on and so forth. And again, thankfully, we at least call these numbers based on what their columns are. 672,513, so on and so forth. Those numbers say the word of the column. So I can apply this construct to any numbering system. What if I work in decimal? Or I'm sorry, not decimal, in binary. So in binary number system, well, let me just go back to decimal for just 1 second. In decimal, if I start counting, I go 0, then I go 1, and I can go 2, 3, 4, 5, 6, 7, 8, 9. Okay, I go to 9, and now I've got 9 ones, right? I've got 9. If I want to go to the next number, I go past my 9, I go to 10. But what is 10 really saying here? If I look at my column structure, the 1 in this column is really a 1 in the tens column. I have a $10 bill, right? I could have 10 ones, but really I have like a $10 bill, or I got 9 ones or 8 ones, so on and so forth. So I've got a 1 in the tens column, and I've got nothing in the ones column. If I said 11, I'd have 1 in the tens column, and I have 1 in the ones column. I have a 10 plus a 1, I get 11. If I had 12, so on and so forth, I would have 1 in the tens column, 2 in the ones column. I have a 10, I got 2 ones, I got $12. So numbering systems can work the same way. So if I think about this, notice this column stops at 9 because I have 10 digits in base 10. Hang on. I have 10 digits in my base 10 numbering system, and those digits are 1 through 9, but I also have to include my starting 0. Not that it goes to 10, but that it actually starts at 0 and goes to 9. When I've used all of my characters, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, using these Arabic numbering shapes, the symbolism, Again, if you look at different cultures, they use different symbolism to equal 1, 2, 3, 4, 5. Some actually use dots and lines, and we could think of Roman numerals or whatever. These shapes, the ninth shape, I'm all out of shapes. If I want to go one more number past 9, I restart my shapes. 0, 1, 2, but then I add 1 to this column. And I can go all the way up from 1 and a 0 to 1 and a 1 and a 1 and a 2 and a 1 and a 3. I can go all the way up to a 9 and a 9. And then I've used all these shapes up. 99. I've got 9 tens, 9 ones, 99. If I want to add one more to this, I've used up all my shapes. I've used my 9 and my 9. I have to restart at 0, but then I put 1 in the next column over. So I put 1 over in this column, and I get 1. Oh, you can't see. Hang on. There we go. 100 and no 10s and no 1s. All right, so hopefully that kind of a preview will help you bridge a gap into binary. So if I look at these, the same idea in, this is base 10, and I'm going to go to base 2, or binary. I start my columns again. Start at 0. Okay, and then I go to 1. It's my next number. And in base 2, I get 2 symbols, 0 and 1. There's my 2 symbols. Just like in base 10, I get 10 symbols, 0 through 9. Base 2, 2 symbols, 0 through 1. I'm out. I'm done. I can't go any further in this column with unique symbols. So just like I did in base 10, when I ran out of symbols, I restarted, and then I increased my next column. So I'm going to do the same thing. I'm going to restart at 0, and I'm going to increase my next column over. Just like I went from 9 to 10, instead of 9 ones, and then the next one I go to 1 in the tens column and nothing in this column, I do the same thing here. I have nothing in this column, but something in this column. And we'll talk about what those columns are in just a second. All right, so now I'm going to increase the number on the right. I keep this number here. So I have 1 in this column, 1 in this column. And I am now full again. So if I go from 1 to the next number, there's no 2. There's no shape 2 that exists in the realm of binary base 2. So now that I'm full, much like I was at 99, 99 was full in decimal, I then have to restart and go to my next column. So here I'm going to restart and then go to my next column. Alright, so I've used up all my digits, 1 and 1, I go to my next column, 1, 0, 0. So 0, 0, 1, 1, and now 1, 0 is 2, and 1, 1 is 3, and 1, 0, 0 is 4, and if I keep going, I increase on the right, but now I got 1, 0, 1 is 5. So if I go to increase this, again, this is full, so I make it a 0. I increase my next column. I keep this one the same. 6. And I increase on the right. Keep this the same. 7. I increase on the right. That is full. That is also full. That is also full. So I got to make all of these 0 and add 1 to the next column over. This one on the right is 0. I can increase and make that a 1. Keep all these the same. There's 9. This one on the right is full, so I make it a 0, increase the next column over. Keep those the same. There's 10. There's 11. If I follow the same pattern, I make that a 0 and I increase that, but I got to make that a 0, so I increase that. That becomes a 1. And there's 12. So if I think in terms of what these columns mean, well, let me write up the columns like I did before. In fact, let me just erase this. And here I had in these columns, base 10, my first column, the 1s column, was really 10 to the 0th. And the 10s column was really 10 to the 1st, and then 10 to the 2nd and the 3rd. So I can do these columns the same way. 2 to the 0th power, 2 to the 1st power, 2 to the squared power, and 2 to the cubed power. Well, what does that really mean? Let me kind of move these out of the way. Should have written smaller. 2 to the 0th power is, anything to the 0th power is the 1s column. 2 to the 1st power, this is my 2s column. 2 squared, 2 times 2, that's 4s column. And 2 cubed, 2 times 2 is 4 times 2 is 8. So these columns in binary are really my 1s column, my 2s column, my 4s column, my 8 column. Much like in decimal, this was my 1s, 10s, hundreds, thousands. So that means if I want to know what any number is in binary, I don't have to do this big long chart and then match it. I can just figure out what each column is and then add them up. For example, let's take this number 6. I have 1 in the 4s column, and I have 1 in the 2s column, and I have nothing in the 1s column. So that means I get a 4 plus a 2 plus a 0, plus, no 1, that gives me 6. Just like if I were to write a big number like 5 in the thousands column and 6 in the hundreds column and a 4 in the tens column and a 2 in the ones column, I just 5 times 1,000 plus 6 times 100 plus 4 times 10 plus 2. 5,642. I do the same thing in binary, like this one right here. I have an 8. I have nothing in the 4. I have a 2 and nothing in the 1. So 8 plus 2 is 10, and you can see it's decimal 10. So I can apply this technique to any binary number. If I had a really long binary number, like this, I can find out what its decimal is very easily by finding out all my columns. All right, 2 to the 0th power, 2 to the 1st power, 2 to the squared power. You can see how this is going to progress. I'm going to run out of room here. 2 to the cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th power. I have 9 binary digits in this. We'd call this a 9-bit binary number because each column is a bit. A bit is a 0 or a 1, so each column is a bit. 9 bits in this, which is actually not very commonly used, but that's okay. So 2 to the 0th power is the 1s column, this is the 2s column, this is the 4s column, this is the 8s column. 2 to the 4th, we just double it. 16, 32, 64, 128, and 256. Do those numbers look familiar to you? 1, 2, 4, 8, 16, 32, 64. It kind of sounds like memory sizes, right? Not a coincidence. All right, so that means if I were to see what this binary number is, this column is the 256, so I have 256. None of those, none of those. I'll take a 32. I'll take a 16. I'll take an 8. None of that, none of that. I'll take a 1. I add it all up. So let's see what I got here. I got 9 out of those. I got 48 out of those. Yeah, drop that down. And that gives me 304. Did I do that right? 8, 9, 10, 11, 12, 14, 9, 1, yep. Plus 9 gives me 313 in base 10. Put a little 10 on the reminder. So this number in base 2 is the same thing as saying 313 in our old numbering system. But computers would see this as 100111001. Okay. So what if I want to go in reverse? What if I want to go from a decimal number and I find out what its binary equivalent is? Well, there's 2 ways you can do it, and I'm going to show you both. One way makes sense to about half of my student population, and the other makes sense to the other half. So I'm going to show you what makes sense to not Mr. Evans-minded kids. Because the way I learned it one way, I was lost. I finally got it now. But the other way I learned it, I was like, oh my gosh, that's so much easier. So some kids like it one way, some kids like it the other. Use whichever one works in your brain. All right, to go. So that's very easy. To go from binary to decimal, we do what's called weighted multiplication. And you can see it's what is the weight of the column. 1s, 2, 4, 8, 16, 32, 64, 128, 216, keep on going. And then if you have it, you take it times 1. And if you don't, you take it times 0. So 256 times 1, 128 times 0, but that ends up being 0. 64 times 0 goes away. Then 32 times 1 is a 32, so on and so forth. That's weighted multiplication. What is the weight of the column? Then you multiply it. Same that we do in decimal. 5 times 1,000, 6 times 100, 4 times 10, 2 times 1, but we're just so used to it when we see this number, we know exactly what that number means. Okay, so that's weighted multiplication. Goes from binary into decimal. Okay, that's what weighted multiplication means. But what if we want to go from decimal into binary? Let's just take the same 313 and see if we get the same binary number. That way we can check our work. All right, to go from decimal to binary, I'm going to use technique number 1. It's called successive division. In successive division, we take our number, 313, that we want to convert to binary, and we're going to divide that number by our base, which in this case is 2. This works for any numbering system. If I want to go from decimal to binary, decimal to something else, I take my number divided by my base, and in this case, I get my result. So 313 does not divide evenly. It is an odd number. So what I'm going to do is I'm going to write the result up here. That would be 150 plus 5 plus 1, 151, 151. And then I have a remainder left over. I have 1 left over, right? Because if it was 314, it'd be 152. If it was 312, it'd be 151. But this is 313, so it's 151 with 1 left over. This remainder is important because this is my first binary bit. This comes over here and becomes my first binary bit. So all of our remainders are going to be our binary numbers. All right, let's just keep going. Now I take my leftover number, 151, and I successively keep dividing it by the base. So 151, so 150 would be 75. And I have a remainder of 1. Did I do this wrong? Something must be wrong because this isn't working right. I must have done my math wrong somewhere because now I have a remainder of 1 again. I know what it is. Well, first of all, it's not 150, it's 160. There we go. This is why I hate doing this. This is the technique I don't like to do in my brain. Hang on, let me double check with the calculator here. Alright, so 256, make sure I did my math right up there, plus a 32, plus 16, plus 8, plus 1, 313. Divide that by 2. Wow, I'm really off. That's why. I know you're sitting there looking at me like, Mr. Edmonds, you're such an idiot. It's been one of those days. 156. Oh, there we go. Because I said 150 plus 5 plus 1. I forgot the plus 5. It's 156. There we go. All right. Well, we all do that, don't we? So 313 divided by 2 gives me 156 with a remainder of 1. The 1 becomes my first binary bit. All right, so now I divide 156. Divide that by 2. So if I take 156 and I divide that by 2, I get a nice pretty 78. And I have no remainder. And yet that 0 becomes my next binary bit. I have no remainder. Now I take my 78 and I divide that by 2. And I get 39 with no remainder. So that becomes my next binary bit. And then I take 39, divide that by 2, and I get 19 and a half. So 19 with 1 left over as a remainder. And there's 1 there. And then I take 19 and I divide that by 2. This takes a while, doesn't it? And I get 9 with a remainder of 1. So I put that right there. And I take 9 and divide that by 2. And I get 4 with a remainder of 1. So I put that right there. Then I take 4 and divide that by 2. And I get 2 with nothing. No remainder. And I take 2 and divide that by 2. And I get 2 divided by 2 is 1. So, and there's no remainder. So I put that there. Now I take 1 and I divide that by 2. And I get 0 with a remainder of 1. And I'm done. I have nothing left. I'm down to 0. So this number here in binary. Let's see if it matches. Where is it? 1 0 0 1 1 1 0 0 1. Hey, it matches. This is 313. So that's successive division. You take your number in the one base and you divide it by the other base, and then you write the remainder. That's in binary, it's no big deal. When we get to other numbering systems later, it becomes a little more complicated. But that's it. You just divide by the base and write the remainder, and you just keep writing it right to left as you divide. That's successive division. Let's talk about the other technique. This is the one that works in Mr. Emmons' brain. All right. Put this down on the screen here. Successive division number 2. All right. This one doesn't really have a name. This is just what I realized you can do, and it's called, I call it, column chooser. Column chooser. All right, so let's say we have our number 313. So what I'm going to do is I'm going to figure out the reverse process of how I found the binary of this. And the binary of this is I looked at my binary columns, right? And going from binary to this number, I looked at my binary columns. Let me get that sheet back up. My binary columns, and I did the weighted multiplication. If I have a 1 in the 1's column, then I put a 1 there. If I have a 1 in the 8's column, I put an 8 there, 1 in the 16's column, so on and so forth. So what I do is I find the columns that I need. How many binary bits would I need to be able to make this number? So I start with my columns. I've got my 2 to the 0th, that's my 1's column. I got my 2 to the 1st, that's my 2's column. So I'm going to make it a little bit bigger so it's easier to see the numbers. I got 2 squared is 4, I got 2 cubed is 8, I got 2 to the 4th is 16, I got 2 to the 5th is 32, I got 2 to the 6th is 64, 2 to the 7th is 128, 2 to the 8th is 256, 2 to the 9th would be 512. Whoa, wait a minute, 512. That's bigger than this number. I don't need this column. I can stop there. 512 is bigger. I'm never going to get a 512. I'm never going to get anything bigger than that. I stop. So that means I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 bits. We're good. I could by all means have a bigger set of columns. I can have more than this number of bits, but everything to the left is going to be zeros. And in fact, you notice how I have all these gaps here? We're totally allowed to fill these in with zeros. Why? Because when we store data, we oftentimes store data into chunks of the same size to make sure I have enough space in physical memory. So in this case, if I'm counting up to, well, at least to 12, then I know I need at least a 1, 1, 0, 0 for 12. I need at least 4 spaces, so I reserve myself up to 4 spaces of memory block. So maybe later I want to change my 12 to a 6. I still have enough space. Even though I'm only using 3 out of the 4 to get at least a 6, I have enough space for all my numbers. So I reserve memory blocks based on how many of these columns do we need. So when you're talking about RAM or ROM or whatever memory space for an actual chip in terms of digital memory, we need to know how many bits do you need. And 4 of these bits, 4 columns, is the same space as 1 byte, because it's a standard unit of measurement, is a byte. So when you're talking about megabytes, you're talking about 1 million of these packets of 4. If you're talking gigabytes, you're talking billions of packets of groups of 4. If you're talking terabytes, you're talking trillion packets of 4. 4 trillion bits. That's a lot of information in a terabyte. All right, anyway, I'm digressing. Let me get back to this. All right, so column chooser method. I want to go from 313 to binary. So I look at this, anything to the left of this is 0 anyway. All right, 256. I got to have that one. I need one of those. So I take 313 and I subtract 256, and I see how much is left over. So if I take 313 and I do the math in my brain, 313 minus 256 is 57. Yes, 57. All right, so I look at the next column. It's a 128. Well, I only got 56. That's too big. I don't need that. 64 is still too big. I don't need that. But 32, I could take a 32 out of that number, can't I? So yeah, I'll take a 32. I'm only allowed to take one because it's binary. If it was another numbering system, I could take out more, but I only take out the 1 because I can't have anything other than a 0 and a 1 in the column. I take out 32. 5 minus 3, that's 2. 7 minus 2, that's 5. I got 25. So yeah, I can take a 16 out of that. And then let me just double check my math here. Yep, so I get a 9. And then I can take an 8 out of a 9. 4 is too big to take out of that 1. 2 is too big to take out of that 1, but a 1 is perfectly okay. Hey, I've checked them all out. Hey, look at this. To me, that seems a lot faster. I have my binary number 1, 0, 0, 1, 1, 1, 0, 0, 1, base 2. This is base 10. So that's the column chooser technique. So now I can do this for any number. I can go from binary to decimal using my weighted multiplication. And I can go from decimal to binary, either doing division and thinking remainders, which again, some of you may like. By all means, use it. Or I could just use my column chooser method and figure out how many binary bits do I need to get to my biggest number, and then just tick them off and subtract them as I work. So hopefully this can help you work through your binary worksheet. If you have any questions, by all means, email me.